So welcome back. Now, have you ever run a regression in Python? For sure you have, but others haven't. So why don't we run a regression through these data points? Basically, for the dummy like me, visualize that there's a negative relationship in that sample between total risk in terms of standard deviation and the average return. All right, so let's just do it. What we do is there are different ways to do that in Python, right? Do some Google, blah, blah, blah. Now I've done it myself. So what we use here, we use the stats models. All right. So the topic here is GLS regression. Why generalized least square and not ordinary least square? Just do OLS if that works for you. We've got a video also on that, the difference between GLS and OLS. It's basically in the assumption of the errors. I don't see the need to assume the IID. So just do a GLS thing. Now we import the stats models.rp and we just call it SM, stats model. All right. Now every regression is like a supervised learning scheme, linear model. We have a supervisor, Y. We have our features, X. Here the supervisor will be the average returns and the features will be a constant and the standard deviation. All right, so here's what we do. X is the inf op standard deviation, and we also add a constant. Yeah? So we take the stats models, and that has the functionality add constants. Add constant, just one constant. All right. And then what's our supervisor here? That's the average return. So it's the investment opportunity mean, so the mean return. All right. Now that's what we have. And now the next thing we need is we are creating an object which I call GLS mu sigma. All right. So we regress mu on the sigma, the mean returns on the sigma. And that will be a stats models.gls y, x. Okay, now the object is created, and now we just fit that thing. So we are saying fit mu onto sigma, and let us take a GLS mu sigma object and just run a fit. Nice. That's what we do. And I don't know whether you know it. There's this directory command which I really like. dir fit mu sigma, and now it shows you what are the functions that that object contains. Right? So you see that you can get different types of standard errors. You can get okay, I just look in that screen. You can get the eigenvalues. You just get everything, yeah? R square, adjusted R square, the residual time series, the T statistics, you name it. All right, yeah, so that I delete again. What I want to print the statistics, the regression table, fit mu sigma dot summary. Yeah. Boom. Let's just magnify it. So what do we see? We see the dependent variable is the mean. We use GLS least square. We had 43 observations, which for statistical analysis is just too little. But doesn't matter, we just did it. The R square is 13%, so kind of 11% of variations in average mean returns in this little cross-section can be explained by the standard deviation. Now, the loadings, I have to look at my screens, but more convenient for me. There's a constant, which we cannot explain which has a 3.5 T statistic, and the slope coefficient is negative. Significance is -2.4. So the 2.5 and 97th percentile are both negative, so it gives indication that there's a negative relationship between the standard deviation and the expected return in the past European data, but we only have 43 observations. I believe these are asymptotic standard errors, and therefore we are far away from the asymptotics with 43. But still, it's okay. It's just so it's marginally significant, let's say. Let's just visualize it in a graph, what that looks like. So we just take the same graph we had, but we are adding the linear regression line. So here's the graph. Yeah, again, let's just save some time. We haven't changed anything on the investment opportunity. No, we haven't. So yeah, let's have the figure here again. So that's what we plot, and we are just adding the GLS line. All right. So we're saying plt.plot. What shall you plot? Plot the investment opportunity information about the standard deviation on the x-axis, and on the y-axis fit mu sigma, that's the object from the fit, and now take the prediction. Take what is the supervised learning or the GLS prediction for these standard deviations. So it's the constant minus the slope or plus the slope, but here it's just negative, it's why I said minus that times the standard deviation of interest. Okay. And now plt.show, so it's over, right? So you here see our mu sigma diagram with the firms, the negative GLS slope. So the data set is special, potentially. All else equal, we would have thought the higher the at least systematic risk, which we don't show here. We just show the total risk. Well, it's a negative relationship. I think you're new to finance. You're like, what the heck? What's that going to tell me? I take on more risk. At the same time, I get lower returns. That's the data set. There's one rescue attempt is about, look at this systematic risk. We might do that in another video. But it shows you one thing, right? It shows you that just in the data, in this European data, if you go for low volatility, you get higher returns. And these are all these low volatility funds, yeah, which had just a stellar performance in the past. Low volatility strategy. Let's just see what comes out of it. Low volatility investment. It's an investment style that buys stocks with low vol. This investment style exploits the low vol anomaly. What's the low vol anomaly? It's the observation that low vol stocks have higher returns than high vol stocks in most markets studied. Interesting. This is an example of a stock market anomaly since it contradicts the central prediction of many theories. But all theories are wrong. Just some are useful, right? I think that's the way to look at the thing. So we have a good data set. We have to say the sums didn't come through, but there it goes. We also see the anomaly in our data set, which is just the best of both worlds. You take a portfolio with little risk and you get high returns. Maybe we have to change the theories. Okay, that's for now.